Hello, welcome, and thank you very much for attending this presentation. My name is José Manuel Campos Salazar, and I'm with the GREP, a research group of the Universidad Politécnica de Catalunya. I am a PhD student. This presentation proposes a multi-battery charger system based on a three-level dual-active bridge power converter. So then, let's get started. As outlined, this presentation consists of the following sections: one introduction, then a battery charger topology, then a control system, then a simulation results to end with conclusion. So let's begin with introduction. As you know, battery chargers are required in many applications, from basic cell phones to complex industrial systems. But at the present, among these applications, it is worth highlighting the importance of the battery chargers for electric vehicles. Battery chargers are typically classified into different categories, and the choice of each of them will depend on the specific needs of the vehicles. For instance, its power supply can be single-phase or three-phase. Depending on the location of the battery charger in an electric vehicle, it can be on or off board. They can also have galvanic isolation or not. From the point of view of power flow, they can be uni or bidirectional. And according to the technology used, they can be two-level or multi-level. Finally, and from the topological point of view, battery chargers are usually implemented with an AC-DC stage connected in cascade with a DC-DC stage. The proposed battery charger is built with two stages, one AC-DC and the other DC-DC. It is powered by a three-phase grid, and it has been designed as an onboard charger. It presents galvanic isolation with bidirectional power flow capacity. And multi-level technology, in this case 3 levels, has been used for its implementation. Now, please let me go to the battery charger topology. Here we have the topology of the battery charger. And as you can see, there are two well-defined stages, one AC-DC and another DC-DC. From the three-phase grid, an AC-DC stage is implemented with an inductive filter and a three-level neutral point clamp or NPC converter, which is connected to the DC link. This DC link is labeled as A-side DC link. Now, the word converter is labeled as a 3L, 3P NPC converter. Following to this stage, the DC-DC stage is connected in cascade. And is implemented with a three-level dual-active bridge topology. This topology included a high-frequency transformer and a second DC link, which is called as a B-side DC link. Its converter is labeled as a 3L 1P DAB converter. Now, each full bridge of the dual-active bridge converter is implemented using NPC technology. Finally, two battery packs are connected, and these battery packs build a battery bank. We also incorporate the resistance and inductance of the wire which are connecting the battery packs. And another thing, both DC links are built with capacitors with their corresponding blading resistors, which are connected in parallel. These resistors are for safety reasons. Here we have the switching model of the proposed battery charger. And please note, all the NPC legs have been replaced by their switching models. And of course, through this switching model, the mathematical modeling of the system was carried out. Now, please let me go to the control system. Here we have the control diagram of the battery charger. And as you can see, we have two control strategies, each for one converter. One for the 3L, 3P NPC converter, and the other one for 3L, 1P DAB converter. The control goals are to regulate the charging current of the batteries IV1 and IV2 by properly controlling the B-side DC link voltages I mean, the voltage of the capacitor belong to these DC links. The second goal is regulate the A side DC link in order to control the total voltage of the DC link, I mean UVDCA, but at the same time keep the balance of the voltage of the capacitor which belong to these DC links, VCA1 and VCA2. The last goal is to regulate the power factor of the weak connection. Now, the control strategy for the 3L3P NPC converter is composed of two controllers, as you can see in the first diagram. One based on oriented voltage control, and another one allows to balancing of the voltages of the capacitor belongs to the A side isolate. On the other hand, the control strategy for the 3L1P DAB converter is implemented with the three controllers. One that balances the control of a VCI and VCI2, as in the previous control strategy, and the other two controllers allow regulating the charging currents through the control of the CM and DM component of the charging current. Now, let me show you some simulation results, please. The simulation model contemplates the following general conditions. The proposed battery charger is connected to a three-phase AC grid with 400-volt RMS line-to-line and with a grid frequency of 50 Hz. Both converters operate with a switching frequency of 10 kHz. The voltage of each battery pack is 400 volts, and the initial condition for the battery charge is the following. The AC/DC link voltage is in balance. I mean, the startup of the system is in the point of view of the AC/DC link is in balance. I mean, the initial voltage of CA1 and CA2 are different, and the initial voltage of the CA1 is 480 volts, and the initial voltage of the CA2 is 320 volts. Now, the total AC side DC link voltage reference is set to 800 volts. The initial charge current are 0, and the reference charge current are IV1 and IV2 and are equal to 5 amps. The initial voltages of the B side DC link, UVCV1 and UVCV2, are imposed by the voltages of each battery, and they are almost equal because each battery pack has a voltage of 400 volts. Finally, the system has been set that both converters are in charge of the A side DC link voltage balancing. That means that both converters can control or can regulate this balance. Now, let me show you some simulation results for the charging currents, for the CM and DM currents, for total voltage of the AC DC link plus each voltage of the capacitor of the DC links, and finally, some simulation for each voltage of the B side DC capacitor. Reference change occurred for charging current. Starting from 5 amps, IV1 and IV2 undergo a step change from 5 amps to 1.1 amps and 5 amps to 3 amps respectively occurs at 200 milliseconds. The other reference change occurs in the total voltage of the A side DC link, I mean UVDCA, at 400 milliseconds and changing the initial value of 800 volts to 950 volts. As you can see, all the dynamic response of the variables present overshoot of less than 20%, except for the current IV2, which present an overshoot of approximately 25%. This allows us to continue improving the timing of the controller associated with it. However, the peak time is less than 100 milliseconds. On the other hand, the settle time are short and are also less than 100 milliseconds. It is important to know that after reference change, the variables are disturbed but quickly reach their reference value before the change. Finally, both converters regulate the balancing of the voltage of the A side DC link capacitor. The associated controller for this balance of the NPC converter is slower than the controller in charge of balancing of this voltage, which belong to the DAB converter. This establishes a coordinate control. Now, please, let me finish with the conclusion. This paper presents a battery charger build with a 3-level 3-phase NPC AC-DC converter and a 3-level dual-to-bridge DC-DC converter in cascade connection. A control scheme has been proposed for the whole system, including the DC-link voltage control and DC-link voltage balance control. Also, the proposed control allows the independent regulation of the charging current of each battery module, I mean AB1 and AB2, through the regulation of the DM and CM component currents. And finally, the proposed battery charger allows fully charging of the battery bank even under different battery initial state of charge values or different battery nominal capacity, without the need to add additional balancing signal. Okay, that is all. Thank you and bye for now.